Again, welcome to DSRT 734 class. In these lectures, we're going to discuss about normal approximations to binomial distribution. This is our second topic in inferential statistics. So our main objective is to determine when the normal distribution can approximate the binomial distribution. Also, how to find the correlation for continuity. Also, how to use the normal distribution to approximate binomial probabilities. So first, the normal approximation to binomial. Here we say that the normal distribution is used to approximate the binomial distribution when it will be impractical to use binomial distribution to find a probability. So again, a normal distribution again can be used to approximate binomial distribution when it's impractical to use binomial distribution to find again probability. And the rule said that the normal approximation to binomial distribution only applies if NP is greater than or equal to 5, and also when NQ is greater than or equal to 5. There are some textbooks that will tell us that when N times P times Q is greater than or equal to 5. But again, some textbooks tell us when NP is greater than 5, and also when NQ is greater than or equal to 5, which both will be the same because everything here will be depend on the sample. So this condition tells us that when the sample size is big enough, we can again do the normal approximation to binomial distribution. When the sample size is very small, we cannot. So again, the N represent the size of the sample, and P represent the probability of success. Q represent the probability of failure, as we know about binomial distribution. The N, the lowercase n, is the sample size, P is probability of success, and Q is probability of failure. So again, some textbooks will tell us N times P times Q should be greater than or equal to 5. Or NP greater than or equal to 5, and NQ greater than or equal to 5. So everything will again will depend on the sample size. As we said earlier, when the sample size is large enough, then we can do the normal approximation to binomial distribution. And the main reason why we do it when it is almost impractical or when it's impractical to use binomial distribution to find probability. So in this case, we have to approximate the normal distribution. So the mean is NP. If we remember this formula in binomial distribution, the mean is always N times P. N is again the sample size, and P is probability of success. We know standard deviation will be square root of NPQ, which is again the sample size, P probability of success times probability of failure. And Q is 1 minus P. So a binomial distribution P equal to 0.25. And here we have some histogram. When N is 4, NP is 1, NQ is 3. So we can see how the binomial distribution gives us. This cannot be approximate to normal distribution, as we can even see the shape of the histogram. This is almost skewed to the right. But we can see that our condition didn't meet. Our condition said NP should be greater than or equal to 5, and NQ also should be greater than or equal to 5. The sample size is only 4, very small. Here we are assuming P is 0.25. If P is 0.25, then Q will be 0.75, which is again Q equal to 1 minus P. Now let's look at our second graph here. We can see that here, this is very good. This can be almost normal distribution, approximate to normal distribution. But we can see the size of the sample from 4 to 10. Now, if the sample size is 10, NP will give me 2.5, NQ will give me 7.5. NQ is okay, but NP is not that good. Now, when the sample size keep increasing, now we have 25. Again, we cannot use this. The reason why, because the condition for NP also should be greater than or equal to 5. But when we compare these two, the first and the second, we can see that again, the histogram is taking a shape of normal distribution instead of skew to the right, the first. Now let's look at the third one. Now the third one, the sample size is now 25, which is way larger than the first and second, 25. So here the NP is what, 6.25, and NQ is what, 18.25. Now we can see our frequency distribution. We have a normal distribution now. And the conditions are met. NP is greater than or equal to 5, and Q also is greater than or equal to 5. Then when we look at the size even increasing more, you can see that the shape is getting more better and more nicer as a normal distribution. So that's the whole concept here. We always can have a normal approximation to a binomial, but everything will be dependent on the sample size, because the condition that will be met is that the n times p should be greater than or equal to 5, and n times q should be greater than or equal to 5. N is the sample size, p is the probability of success, q is the probability of failure. So q is equal to 1 minus p. So as we said, as n increases, the histogram approaches a normal curve. As we can see the 4 examples here. The first one, again, the n was too small. So even the shape is almost skewed to the right. Second is approaching to normal, but still the condition has not met and it doesn't look that good. But when the sample size went to 25 and 50, you can see we have a normal curve now. So let's try one example. So the example here is how to approximate the binomial. So here they say we should decide whether you can use normal distribution to approximate X. That is the number of people who reply yes. This problem is supposed to be discrete because the number of people who reply yes is binomial, yes or no. The outcome is 2, and also the random variable is discrete. We know normal distribution, the random variable is continuous and it's based on measurement, not counting. But as we saw the rule here, when NP when NP and NQ are greater than or equal to 5, we can approximate it. So now let's see the question here. They say 51% of adults in US whose New Year resolution was to exercise more achieve their resolution. Again, 51% of the adults in US whose New Year's resolution was to exercise more achieve their resolution. That 51% achieve it. Now you randomly selected 65 adults in the US whose resolution was to exercise more and asked each if he or she achieved that resolution. So now our main concern is what is N, what is P, what is Q. 51% achieve. So 0.51 is our P. If I know the P, then of course we know the Q. The Q is 0.49. Then when we look at the question, is 65. So the size is 65. Let's go back to the question. The question says, you randomly select 65 adults in US whose resolution was to exercise more. But based on previous studies, we know that 51% of adults, so that's P. P is 0.51. If P is 0.51, then Q will be 0.49. So now we want to decide whether we can use the normal distribution to approximate the X. So now we have to test the NP and NQ. So we saw that NP will be 65 times 0.51 and Q will be 65 times 0.49. Both answers are greater than 5, so we can approximate it. So here, so we can use the normal approximation. Again, why the Q is 0.49? Because the question says 55% were, and if they decided to exercise more for their New Year resolution, 51% are successful. So 51%, we change it to decimal value, it will be 0.51. So that will be our p-value. 65 sample size, adults. So that is the sample size. So we test our NP and NQ since they are greater than 5, then we can use the normal approximation. So the mean will be again NP, which is 65 times 0.51. That gives us 33.15. Then our standard deviation will be square root of NPQ. So we get 65 times 0.51 times 0.49, and that gives us 4.03. Now, in some textbook, we only test NPQ should be greater than or equal to 5. And when we do the same thing, we should get the same. The answer should be greater than or equal to 5. Should be greater. So even we test NPQ alone or NP and NQ, we can still use the normal approximation because NPQ will be greater than 5 also. Should be around somewhere 16 point something. As we can see, square root of NPQ is 4.03. So let's try a second question here. The second question again, we're still on approximating the binomial. So the second question again said, decide whether you can use the normal distribution to approximate X. The number of people who reply yes. If you can, find the mean and also the standard deviation. So the question here said 15% of adults in the US do not make New Year's resolution. So you randomly select 15 adults in US and ask each if he or she can make a New Year's resolution. So first thing, we are going to test our NP and NQ. The sample is 15 adults, so N is equal to 15. And also we said 15%. Let's go back to the question again. 50% of adults in US do not make New Year's resolution. So our P is 0.15, 15%, 0.15. If that is the case, Q will be 0.85. Then we randomly select 15 adults. So N will give us 15. So now let's test our condition. N times P is 15 times 0.15. That gave us 2.25. It's less than 5. Then NQ is 15 times 0.85. It gives us 12.75, which is greater than or equal to 5. But again, here both NP and NQ must be greater than or equal to 5. So we cannot use the normal approximation. And the same thing, if we find the NPQ, our answer surely will be less than 5. It's to be less than 5. And again, we're going to do that when we find this. So because NP is less than 5, you cannot use the normal distribution to approximate the distribution of X. Now, let's see. We have 0.15 times 0.85. I'm going to use the calculator here. So 0.15 times 0.85. And we know the sample size is 15. So this will be times 15. And we can see the answer is 1.91, which is again less than. So what I'm trying to say here is that either you use NP and NQ or NPQ, the conditions, the result will be the same. So again, one more time, we have the sample size 15 times 0.15, which is the P, times 0.85, which is the Q, we get 1.9. So here again, we can say that we cannot use the normal approximation because NPQ will also be less than, again, 5. So we move to the next section, the correction for continuity. Here we say that a binomial distribution is discrete and can be represented by probability histogram, since it's a discrete based on counting. Because histogram, our x-axis is the class, and it have to be a whole numbers. So here we say to calculate exact binomial probability, the binomial formula is used for each value of x, and then the results are added. So we know the formula will be the combination of n and x. S is our random variable, whatever amount. N is the size of the sample. Then p to the power x. P is the probability of success. Then q to the power n minus x. So based on this, whatever the s value is, we can, that's why I say, to calculate exact binomial probability, the binomial formula is used for each value of x. So let's say the first s is 10, 15, 20, 0, or whatever, we can calculate each probability. Then if we have to add it, we add all together. So geometrically, this corresponds to adding the areas of bars in the probability histogram. So let's say we are looking for the probability that x is less than or equal to 5, and we are assuming the arrow here is 5, and the whole thing is 10. So if I can find the probability when it's 1, 2, 3, 4, then the last one, then we add all together. Or let's say I'm looking for probability that s is 9. If s is 9, I don't want to find 1, 2, 3, 4 up to 9. So what I will look for is I will find the probability that the x is 10. Then I will subtract that and this section, the whole 10, to get this part. And say, let's say this is 9. So we subtract one part to get the rest. Again, we may solve an example soon. So when you use a continuous normal distribution to approximate a binomial probability, you need to move 0.5 unit to the left and right of the midpoint to include all possible s values in the interval. That's the correction for continuity. That's the whole concept here. You see, in probability, again, I can find any x value, the probability of any s value in the boxes. But when we are using continuity, we move 0.5 to the left and right. And we normally in histogram too, we can be in the middle here. We say the middle of the bar is called the midpoint, which normally is the average of the beginning value and the ending value, and that will give us the midpoint. But again, when we are using continuity, again, binomial is discrete, so the values are solid, finite. Now, when you use a continuous normal distribution to approximate the binomial probability, we always need to move 0.5 unit to the left and right of the midpoint to include all possible s values. And that's the example. You have C right here. I include C plus 0.5 to the left, C minus 0.5 to include every. So now using a collection for continuity, let's see an example here. Here they say use a correction for continuity to convert the binomial intervals to normal distribution interval. Now, the probability of getting between 270 and 310 successive, inclusive including the 270 and 310 itself. The discrete midpoint values are 270, 271, 3, 2, 4, 5, up to 310. So 270, 271, 272, 272 up to 310. That will be the discrete values. Now, the corresponding interval for the continuous normal distribution is, we start 270, so we get to the left 269.5, and to the right 0.5 will be 310.5. And that's the whole concept we are trying to say here. Move 0.5 to the left and to the right. Then the probability of getting at least 158 successes will be the discrete midpoint values are 158, 159, 160, 161 to going. Now, the corresponding interval for the continuous normal distribution is x is greater than 1.57. The reason why, again, we move to the left, so greater than 157.5, or the 60, 61, 62, we keep going. We say less than 63, so excluding 63. This is discrete midpoint. 60, 61, 62. That's where we can't go 62.34 is counting, because there's a probability of getting less than 63. So this means I reach 62, I'll say S should be less than 62.5. We had, again, 0.5 to the right. So using normal distribution to approximate binomial probabilities, the first thing, we have to verify that the binomial distribution applies. This is where we have to state the condition NP greater than or equal to 5, NQ greater than or equal to 5. So we have to specify the N, P, and Q. Then we determine if you can use the normal distribution to approximate X. So check the condition. Is NP greater than or equal to 5? Is NQ greater than or equal to 5? If it's true, then we find the mean and the standard deviation for the distribution. Remember, why do we find the mean and standard deviation? Because in normal distribution, when we're covering the normal distribution, there's two main parameters for it. The mean, which is always in the center of the normal distribution, and then the standard deviation. So if I'm finding the probability of some random variable using normal distribution, I need to find a z-score. Then the z-score will be the value, the probability of that random variable value, which is x, minus the mean over the standard deviation. So that's why it's very important that when we are using the normal distribution to approximate a binomial probability, normal distribution, we need the mean and the standard deviation. So first, if this condition is met, because in the binomial question, the N will be given, the P will be given. Always, we saw that in our probability lectures. The N will be the number of the tries, S is what we are looking for. Then P is the probability of, so if we know P, then we know Q, because P again will be, Q again will be 1 minus P. But if I'm going to solve this problem using normal distribution, then I need to find a Z value. And the Z formula is the random variable X minus the mean over standard deviation. So we need to find the mean. And the question was a binomial. So we know again from probability that binomial, to find the mean, is N times P. To find the standard deviation is N times P times Q square root. And when we have these two values, we can easily find a Z value and find the P from the standard normal table. So those are the three steps. And the last step, again, that's where we do the correction of continuity. Apply the appropriate continuity correction, which means we had 0.5 to the right and subtract 0.5 shifted to the left. Then shade the corresponding area on that curve for normal distribution. And this is what, let's go back. So this is how the graph will look like. So it will look something like this now. So we have a C value, can be any value, let's say 100. So shift to the left, we start, because in a normal distribution, we have to find the area under the curve. So if you have one value, we shift to the left, to the right, then we get there. So now we know the condition has met. We know the NPQ, the condition has been met. We find our mean, we find our standard deviation. Then we apply the shaded area in the normal curve by subtracting to the left 0.5, adding to the right 0.5. Then the next step is to find a Z value. So the Z will be the random variable S minus mu over standard deviation. Then after that, we go to our table, use the standard normal table to find the P. So let's try one example. Again, approximating a binomial probability. The question is given. This is almost probability topic. In our probability, the question is given and they will specify whether it's a normal, whether it's binomial or any distribution. But this question is given as binomial. But based on the condition of NP greater than or equal to 5, NQ greater than or equal to 5, or NPQ greater than or equal to 5, if that condition is true, then instead of using binomial formula, we solve it using, again, a normal distribution steps. So here we have 51% of adults in US whose New Year resolution was to exercise more, achieve their resolution. So 51% of adults in US whose New Year resolution was to exercise more, achieve their resolution. You randomly selected 65 adults in the US whose resolution was to exercise more and asked if he or she achieved their resolution. What is the probability that fewer than 40 of them respond yes? So you can see this question is probability. First, the outcome is what? Yes or no. Second, the random variable S is what? Discrete, counting. How many adults? So this is a Z question for probability, but we can say, okay, we want to approximate it and use normal probability steps to solve it. So this is where we have to check our conditions. So can use the normal approximation. We say we should see this slide. And the reason that was the previous slide we saw, because when we find the NP is greater than or equal to 5, and the NP was 65 times 0.51. NQ was also 65 times 0.49. And both of them give us the answer greater than or equal to 5. So if we know that, then we're going to find that actually this is the mu. The NP will give us 33.15. And the NQ will be a little bit less than 33.15 because it will be 65 times 0.49. So since NP is greater than or equal to 5, NQ is greater than or equal to 5, we can find the mean and standard deviation, because in normal distribution, the two main parameters are the mean and the standard deviation. So if we get the mean and standard deviation, we can find the Z-score. Now, we apply the continuity of correction because based on the question here, they say, what is the probability that fewer than 40? So we are looking probability that X is less than 40, not less than or equal, but fewer than 40, so less than 40. So we use our continuity correction. Since we're in 40, we're going to, the shaded area will be 39.5 to 40.5. Subtract 0.5 to the left, add 0.5 to the right. So this is where we have our 39.5. So now we go to the table to go and first we find a Z value. So when we find a z value, we go to the table. The value we get in the table P will be from the left to this value. And that will be our answer because it's less than 39.5. So now we look for the z. Z will be x minus mu over standard deviation. Now instead of using 40, we use 39.5 minus 33.15 over the standard deviation we find in the previous slide was 4.03, and we find the mean to be 33.15. First thing, we check the condition of NP and NQ. Both are greater than or equal to 5, because NP will give me 33.15, NQ should give me somewhere around 31 or so. So we do the continuity, we get a shaded area, we find a z. Now when we find a z finish, the z is 1.8, so it will be at 39. We find the x was 39.5, so the z will be at that position, while the mu is 0, the center. So we go to the table, and when we went to the table, we find that is the standard normal table. We find the p-value under 1.5 and 58 to be 0.9429. Again, to the left, less than, so this will be our final solution. The next example said, a survey reports that 86% of internet users use Windows Internet Explorer as their browser. You randomly select 200 internet users and ask each whether he or she uses Internet Explorer as his or her browser. What is the probability that exactly 176 will say yes? Again, this is binomial question because the outcome is either yes or no. And also the random variable is based on counting. What is the probability that 176 will say yes or no? So this is binomial. But can we approximate it, approximate a binomial probability to use normal probability? Now, let's check. First, the condition, NP should be greater than or equal to 5, NQ should be greater than or equal to 5. The survey report that 86 of the internet users use Internet Explorer as their browser. So this means, and also you randomly select 200. So this means N is 200, P is 86%, which will be 0.86. So Q will be 0.14. So we're going to check our condition. NP will be 200 times 0.86, 172. That is greater than or equal to 5. NQ also is 200 times 0.14. It's 28, so it's greater than or equal to 5. So this means we can go ahead with the normal distribution. So if that's the case, with the normal probability, we need the two important parameters, which is the mean and the standard deviation. So we find the mean to be NP 172, and the standard deviation square root of NPQ is 4.91. So if I know the mu and standard deviation, next I'm going to apply the continuity, the correction. So here, what is the probability that exactly 176 we use yes or no? So 0.5 to the left, 0.5 to the right. So it's 175.5, 176.5. This time we are including to the right because they say exactly 176, exactly 176. So we have to increase to the right, decrease to the left, 0.5, 0.5. Now, if they said less than 176, then we're going to only use 1.75.5. We don't have to go to the greater section. That was our first example. So here we can see we have 176.5 and 175.5, the shaded area here. So this is what we are looking for exactly. And so when we go to the table, now we find a z value. When we find a z value, we go to the table. We are going to find the value from left to 175.5, then from left again to 176.5. Then we find the difference of the two probability because this time we are looking for the exact 176. So it will be the shaded area. If it's less than 176, then it will be to the left, everything to the left. So that's why, again, in the first example, we look for only one p-value. Then when we get the answer, it's from left. So now if it's greater, then we get only one p-value still, but to the right. So when we get the answer from the table, which is the standard normal table, we have to subtract the answer from 1 to get the p. But if it's exactly value, then now we have two parts now. 0.5 to the left, 0.5 to the right, subtract and add it. So first we find the Z1. Z1, we are using the 175.5. Again, the reason why we are doing this, because we are looking for the probability that exactly 176 correspond. So exact value, we have to subtract 0.5 to the left, 0.5 to the right, and get the twos and the shaded, this is the shaded area we are looking for now, between 175.5 to 176.5. Now, if it's less than 176, then we are looking from 176, let's say to be 175.5 to the left alone. So the answer we get from the table, that's it. If it's greater than 176, then we are going to look 176.5 to the right alone. And to the right means what we get in the table is to the left. So we subtract that answer from 1, then we get it to the right. So now we get a Z1 value, 175.5 minus 172 divided by 4.91, and that gives us 0.71. So this is our first Z value. The second Z value using 176.5 minus 172, 4.91, we get this value. Then we find a P for both of them. So when we get a P for both of them, we subtract it. And that's what is the next. So we get a P of the first one, 0.8212. Then we get a P of the second one, 0.7611. So we find the difference of the two, 0.8212 minus 0.7611. So our final solution will be 0.0601. So we can see how this problem was. Very nice problem. Let's go back to the beginning. We are solving this problem, but this problem can be solved using binomial. But we want to approximate it to use normal distribution instead of binomial. But when we read the question, it's a binomial question. The P is 86%, which is 0.86. And they say 86% of internet users use Windows Explorer, Internet Explorer. They give us a sample, 200 internet users, so that will be our N. What is the probability that 176 will say yes? So again, that will be our random variable X, which is discrete because it's based on counting how many. So we can use the binomial formula. But sometimes binomial formula using makes it very complicated. So I want to see if I can use the normal distribution. So first, we check the condition. Is NP greater than 5 or equal to 5? Yes, it's 172. Is NQ greater than 5? Yes, it's 28. Okay, if the condition is met, then I'm going with normal distribution. I need a standard deviation and the mean. So we find the mean, we find the standard deviation. We do the continuity correction. Again, we're looking for the probability that exactly 176. So to the left is 0.5, we subtract. To the right, we had 0.5 to it. Now, as I said earlier, if the condition said greater than 176, then we are going to use only 176.5. If it's less than 176, then we are going to use only 175.5. So in that case, the answer we get for the P will be from left to the 175.5. But if it's greater than 176.5, the answer we get in P will be from left to 176.5. So we have to subtract it from 1 to get from 176.5 to the right of the normal curve. So since it's exact, again, we have to So we have our normal curve. So we come up with the z values, and we get a z for the first 175.5 random variable. We get a z for 175.5, 176.5 also. And these are both of them here. Then we look for the p-value for both, 0.71, 0.92. 0.92 p-value is 0.8212. Then 0.71 p-value is 0.7611. We are looking for this shaded area, so we have to subtract the long one, which is 0.92 p, which is 0.8212, minus 0.7611. And that will be our final solution. So again, in summary, in this section, we learn how to determine the normal distribution, to approximate it using to binomial, also how to find the correction for continuity, and how to use the normal distribution to approximate again binomial distribution. So again, wish everybody the best. Thank you. Again, you can comment on these lectures, like or subscribe it. I'm going to again upload it to my YouTube channel. Thank you.